Hello friends, in this session I'm going to take up the non-binary ripple counters. So let's start with the other completion of basically our counters topics. So the non-binary, now why the term non-binary is associated with it? Since when we said that we are trying to formulate, or we are trying to construct a 3-bit ripple counter, what we did was we just counted it in a normal counting fashion, like 0, 1, 2, 3, so on, right, in the bars like we do it in binary counting. So that was a simple binary counting technique. But now when I talk about non-binary ripple counter, it basically means that the order may not remain the same as binary counting. The order may be some random one. Now what do I mean by random one is basically it could be a gray code counting or BCD counting. Now BCD counting, the BCD counting starts from 0 and still 9, and then you don't go to 10. It's basically a combination of all the bits that you had from 0 to 9, right? So that is an example of non-binary counting. Some other examples could be sequential counters, gray code counting, etc. So let's start with the BCD counter, which is an example of this. Now BCD counter is also called a special case of decade counter. Now why is it so? Decade counter, as we also discussed, maybe slightly we discussed in the previous session, that decade counter is one which has 10 stages in it, and now 10 stages means that it can be any 10 stages. Now first of all, when I have 10 stages, when I'm talking about 10 stages, then when I'm talking about 10 stages, let me see that how many flip-flops I'll be requiring for it. Now since it is 10 stages, just forget about this order for now. So when it has 10 stages, I'll be needing at least 4 flip-flops, because 3 flip-flops will only be able to give me 8 stages, right? 2 to power 3 is 8. So with 4, I'll be able to get 16 stages, and I'll be only using or utilizing the 10 stages from it. Now which 10 stages? Now that 10 stages could be anything, let it be from 0 to 9 if I'm using, then it becomes your BCD counter. But otherwise, I can also use any other 10 stages from the count of 0 to 15, right? So that is the basically difference between your BCD counter and your decade counter. Decade counter can use any 10 stages from that 16 stages, but BCD counter specifically uses those 0 to 9 counting part, right? So once this is clear, now we go to the construction. The construction of BCD counter is very simple. It is very similar to the previous ones that we have already discussed, ripple counter, 3-bit ripple counter. But now we have what? We have 10 stages. So we have 4 flip-flops. We have 4 flip-flops attached in the similar manner. Now the important thing over here is, the difference that you may note is this clear bit. Now clear bit is used to clear the contents of the flip-flop. Now as I told that this is going to use 4 flip-flops and it's going to have 16 stages, 0 to 15, but since I need to choose only from 0 to, I need to use only from 0 to 9, then what do I want? I want that at the 10th stage, at the 11th stage, that is when it counts to 10, it should not count to 10, it should, it should become 0. That is, it should repeat the cycle. So in order to repeat the cycle, what will I have to do? I'll have to clear the contents on the 11th clock pulse, because at 11th clock pulse I need the entire thing to act as 0, 0, 0, 0. So we'll discuss it in detail in a short while, but in order to clear the contents, we require the clear things over here, clear bits. So we've used it over here. Now there are 4 flip-flops, JK flip-flops. Now since the ripple thing works only in toggle mode, as we discussed in the previous sessions, we have attached the input as 1, 1, and since it is ripple, so what is happening is only the first one is supplied an external clock pulse and the other ones are getting the clock pulse from the outputs of the previous flip-flops. Now let's move on to the stages and then we'll discuss this again. We'll come back to this. So the stages are like this. Initially we have 0, 0, 0, 0, and what will happen is, now again this is also negatively edge triggered, and you know what is a negatively edge triggered, that the flip-flop will only get triggered when the clock pulse changes from 1 to 0 and not from 0 to 1. And since this is the last one, Q0, which is the lowest significant bit, so this is being supplied from the external clock pulse, so this will be going to be changed at every clock pulse. So this is what is happening over here. We have 0 1 0 1 0 1 0 1 so on at every clock pulse, but this one will only get triggered when this changes from 1 to 0. So this changes from 1 to 0, this gets triggered. Now this does not get triggered because this is 0 to 1 still. Then this is 0 to 1, this remains same. 1 to 0, this gets triggered. Now this is 1 to 0, this gets triggered, right? So this is very similar to the one we discussed in the previous session, which is 3-bit ripple counter. Up and down we had discussed both, so you may please consider watching them. They are attached in the same playlist. So what we do over here is, yes, the important thing that I had to come was that after this 9th clock pulse, now how many stages have we encountered till this? This is 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th. This is the 10th stage. Now what do I want after this? I want again the first stage to repeat, which is 0 0 0 0. So for that, what would I need to do? I would have to change this and this to 0, right? Now how do I change this and this to 0? Maybe I can apply some clear thing. I can apply some digital operation, let's say some AND operation with 0 or a NOT gate, anything, right? So for this we use the clear clock pulse. Now we'll come back to this. So what do I do over here is, the first and last bit needs to be changed to 0, right? The first and last output bit needs to be changed to 0. So I insert the last bit from here, the last bit and the first bit, both are input to this AND gate. And what do I input along with this? I input the NOTs of what? The NOTs of the 2nd and 3rd flip-flop. So the 2nd and 3rd flip-flops NOTs were what? They were 1 1, because they were the outputs were 0 0, so NOTs would be 1 1. Now we AND all these, and the AND of all the ones will be 1, and we insert this in the clear bit of all the flip-flops. Now what would this do? This will set the clear bit of all the flip-flops, and this would clear all the contents of all the flip-flops over here. So that is all we wanted, and this is how we perform it. So I'm just repeating it once again. The last bit and the first bit's outputs are taken, and the 2nd and 3rd bits NOTs are taken, because the 2nd and 3rd bits were 0 and we are taking the 1. So ones will be getting only if we take the NOTs, right? And the entire thing then becomes 1. If I would have chosen these, the product would have become 0, and I want to set the clear bits, right? So I'll have to insert a 1 over there. So that is the reason why I'm taking the NOTs of these and the original outputs of these. So with this, what we do, with this we clear the contents of our flip-flop and the entire thing repeats again. So we already discussed this. We've already discussed that BCD counter is a special case of decade counter, and output frequency of BCD counter will be what? That will be Fn by 10, since it has 10 stages. So that's all for this session. In the next session, I'll be taking up the ring counter and the Johnson counter. Again, a very important concept from the perspective of counters. So stay tuned for more good work coming up. Thank you.